Welcome to this sixth lecture video for Physics 4A. In this lecture, we outline a problem-solving strategy that you will be using to solve force analysis problems for the next few weeks of this class. Moreover, this multi-step problem-solving strategy is a paradigmatic example to follow and use to fashion your own problem-solving approaches as we introduce mechanical concepts beyond the force and learn to solve more complex situations. We will start by introducing the four-step standard strategy using the example of Atwood machine, and then we apply it to two more one-dimensional examples. As the third step of the standard strategy can only be illustrated with two-dimensional examples, we use the examples involving inclined planes and pulley in the second half, demonstrating how this multi-step problem-solving strategy helps approach situations where intuitive problem-solving often fails. Finally, as you will find the different versions of Newton's law problem-solving strategies, standard strategy just being our version at the College of Alameda, I will draw comparisons between our strategy and the one you will find in the textbook, and the one you will find in Andrew Elby's portable TA.
So let me do this as a way of introduction. So if we are dealing with this question, and if I had asked you, what does the scale read? Most of you would have answered 180 pounds right away, right? That's where going through all this looks maybe even extraneous, because you have a good intuitive feel for what the answer should be. So the method that I'm going to introduce now are for the questions where you don't have intuitive answers. So, what we did here is actually kind of like a standard strategy. A bit haphazard, but kind of like standard strategy. You might have felt it's unnecessary. And, to an extent, yeah, that's right. You could have answered this in 1 minute instead of taking 15 minutes. But it's for the questions where if you're just staring at it, questions that you wouldn't be able to answer in a year, or, you wouldn't be able to answer for many, many hours. That standard strategy will give a way to approach it within 20, 30 minutes or less. So this is an example of the problem from your worksheet. Problem 10, Atwood's machine. So, you can read the words in it if you want. The key part is this. So you have this device here. That's a pulley. Everyone here knows what a pulley is? It's, it's some circular wheel-like thing. It's pivoted here, and it's free to rotate one way or the other. So I have a pulley here, and what this problem is saying is that there are two masses here. They are connected by string to each other, mass 1 and mass 2. And this is the question. It walks you through, but the key question is this. When you let go of these masses, will they move? If you have a pulley, unequal masses, intuitively they will move, right? Okay, let's say M1 is, it looks as it's drawn. M1 is heavier. Then will this one be the one that accelerates downward? And M2 will accelerate upward, right? So will they have the same magnitude of acceleration? Okay, you can answer all that intuitively. Now this is question. So what is amount of that acceleration? So this is the question that maybe some people can answer intuitively, but most people will have trouble now answering intuitively. If you're just trying to answer that in one single leap, you might say, I don't know, A equals G. How many think this might be the correct answer? Okay, you have good intuition. You at least recognize that's not the correct answer. All right, so how do you get to the correct answer then, if it's not equal to G? No? Minus what? Minus. Well, I'm looking for magnitude. So I'm looking for a positive answer. So G and minus G are essentially the same. Mg, that's not even the right quantity. Mg is force. A is acceleration. right? I'm looking for a quantity that has a unit of meters per second squared, not newtons. So let me write down the correct answer. This is the correct answer. And see how many of you would have guessed it. It's on honor system. So the correct answer, when we go through all these steps, will be this. Acceleration is equal to m1 minus m2 divided by m1 plus m2 times g. It's a surprisingly simple answer. How many of you would have guessed that? Yeah, you didn't guess the bottom, right? Yeah, so you recognize that there's a difference in forces. That's where you might even guess m1 minus m2 here, or m1g minus m2g. But you know that that's a force you need to get. So, what I'm trying to point out here is that eventually, very soon, today, in this class, you're going to run across a question where you cannot intuitively guess your way through. And what we are introducing now is for that situation, which you will face starting today. So far, you have been able to answer physics questions without having any systematic approach to it, because we are really relying on your intuition so far. And what I'm telling you is that intuition is going to begin to fail. And as that intuition fails, we want to give you a set of tools to build a new set of intuitions. I have the answer memorized. You could call this kind of intuition. I've done this problem, not hundreds, dozens of times that I have them memorized. That's just kind of an intuition, but that's something you have to build. So that's not something you are born with. So let me I'll leave the diagram up there for actual demonstration, but let me go back and project this. These set of steps are what's called the standard strategy. So I'll leave those words there if you want to read it, but I will also say as I'm writing it down here. So what we are going to call standard strategy. Do I actually want to project anything? You guys all have the worksheets, right? Let me not project anything. I think it's more distracting than it's helpful. So let me put this here. All right. So what I'll do is I'll write the steps of the standard strategy here. And as I'm writing that down here, I will work through this problem. Can someone tell me what problem number this was? Worksheet 3, problem 10. So, I'm not going to go through exactly parts A, B, C, but the steps I'll go through will roughly match that. So here the key question we are asking is, what is the acceleration? And the standard strategy is the set of steps that are designed to answer that. So let me start out with the statement of the standard strategy. So it's a 4-step process. Depending on the textbook, sometimes it's broken out in a different way. In this class, I'll say it's 4 steps. This is unlike Newton's laws, where there's only Newton's 3 laws of motion. These steps can be broken down into different ways. But the 4 that I have is the one that makes logical sense. So let me write down 1, 2, 3, 4. So the first step is you draw your free body diagram. And this single two-word phrase serves as a reminder, actually, because this is something you will need to do as you are drawing your free body diagram. Free body diagram, it's not just you are not doodling, you're not just drawing a sketch. It's your problem-solving tool. So your free body diagram reflects your understanding of the problem setup. So what you are really doing here is you're understanding the problem setup. And you've been doing this with the kinematics too. What's different about free body diagram is it's a particular type of diagram that people have found very useful in doing force problems. So here, let me draw the free body diagram for this. How many free body diagrams would I need? 2. I need 1 for each object. So I need 1 for M1, I need another for M2. So as I draw my free body diagrams, I need to label M1 and M2. So let's go through this quickly. Okay, what are the forces on M1? And we can start out with the weight. So the reason I like to do that is weight is always there. And I like to make my free body diagrams as minimal as possible. I only draw a force if I recognize that it must be there. So things like air resistance, friction, I don't even consider them ever because Like nothing forces me to write them. So they both have weight. So there will be m1g of force pulling m1 down. And there will be force of m2g pulling m2 down. All right, this diagram is clearly not complete because m2 we think it will be accelerating upward and not downward. So what other forces are on m2 that's making it accelerate upward instead? That's tension. You know that because there's a string attached to it. So, all right, so there's going to be tension upward. Let me call that T2. Does this look like a complete free body diagram? It doesn't? What forces are missing? I'm talking about M2. Oh. Yeah. So when you're talking about free body diagram, the idea is that you should be able to ask yourself, is this complete for each object by itself? Because any interaction you have between objects, Newton's third law is going to take care of that. So if this object participates in any interaction, it should show up in this diagram itself. So looking at M2 by itself, it looks like a complete free body diagram, right? We haven't missed any force. And in fact, there's no other force we can draw. String is the only thing touching it. So there's no other force that can be on it. So it's M1 that, as you look at it, so Joseph, why did you think this was not complete free body diagram? Okay, so what you're saying is that between these two?
No, between the M1 and
string, yeah. So you see the string is attached, and your intuition says that this is probably going to be taut. So that means there must be some kind of tension force. Right? Let me impose on your intuition one more. These two tension forces, T1 and T2, how do you think they are related? T2 is? Smaller than T1. Okay, that doesn't turn out to be true. So somebody with a better intuition. So I'm asking for something that I haven't touched. This is something that you're trying to guess. And what intuition means is that as you make a guess, you're guessing correctly. That's what intuition means. Everyone comes with a different level of intuition. Joseph has hand raised. Anyone else? Jared? That they are the same? Yeah, does everyone have that sort of intuitive feel that you think these two tensions might be the same? Yeah, one thing you can point to is that, well, it's a one and the same string, so maybe they'll be the same. And turns out that's not actually the condition. So the condition, you're going to see this in problem a lot. And I will explain later why this condition matters. So the condition is actually on the pulley. So for the pulley, we need to be able to say these two things. One is that they are frictionless. That seems clear on its own, right? If there's friction, then pulley might refuse to turn. So, frictionless. And here's the second thing that's difficult to understand at this moment, but in about 2 months, we'll go over that. It must also be massless. So provided that those two conditions are met, if these two conditions are met on the pulley, then this will be true. And we don't like, at least I don't like complicated problems. So most of the time, I will, even when I don't say it explicitly, you can more or less assume this. And we can say, all right, these are the same tensions. I'm just going to use one letter to label them. So that's a drawing free body diagram. This now looks like a complete free body diagram, right? Yes? Okay. So that's a drawing free body diagram. As you can see, it's taking a lot of our time. And there's a reason for that. This is the most important step. You do this step wrong, and it doesn't really matter what you do in the next 3 steps. And the problem solving, you're just going to get it wrong. If your free body diagram is wrong, you're done. There's nothing you can do from that point on to get the correct answer. So this is the most important step. Make sure you spend enough time doing this correctly. Once you have free body diagram, then the rest of the steps build on it. The second step is you have to define coordinate axis. And I'll give you one rule that's useful in many, many situations. As you're defining your coordinate axis, you are really looking at one particular quantity. You are looking at the direction of acceleration. This especially matters for 2-dimensional problems. Right now, today, we are dealing with a 1-dimensional problem, so maybe it doesn't matter as much, but direction of A. So what you really want to do as you define your axis is you want to make sure that A is parallel with either X or Y. So it's parallel with one of the two axes. So, in our problem here, it's a one-dimensional problem, so that's not really a big deal. So let me just make it simple and say, all right, I'm going to say just the upward is positive. Actually, let me do it. Let me do it this way. Instead of trying to define one coordinate axis for both the free body diagrams, I'm going to say that, you know what? I have freedom to pick coordinate axis for each free body diagram separately. So I'm going to say for this free body diagram, where the object will be accelerating upward, I'm going to say, you know what? Upward is my positive. And for here, where the object will be accelerating downward, according to our intuition, let me say, you know what? Downward is going to be positive. And this choice will influence how we go through next steps, but that's a perfectly valid way to do it. So let me go through the rest of that with that in mind. Third step, we are going to skip that for now. What the third step is, I'll write it down, but I won't do anything with it. You break down forces into components, as in x and y components. So this is something that matters for two-dimensional problems. That's a one-dimensional problem. I have no forces to break down into components. Okay? And before I write down the fourth step, I really want to emphasize this aspect of physics problem solving. Have I written down a single equation? I haven't. And really, I want to emphasize that because that's the most common mistake students make. You jump on ahead too quickly into writing down a formula. Don't. Make sure you understand the setup first. Make sure you set up the proper parameters for the rest of the problem solving. You only write down equations when you know what you are doing. You don't write down equations without understanding what's going on. That's why it's the fourth step where you actually write down your first set of equations. In the first step, you write down Newton's second law equations. You write down net force is equal to mass times acceleration. So that's the very last step in standard strategy. So standard strategy actually doesn't solve the problem for you. It sets up a set of equations which you can now solve, hopefully, to get the answer to your question. As you write this down, let me just point out two things you should watch out for or remind yourself. You write down equation for each object and for each direction or each dimension. As in, so right now this is a one-dimensional two-object problem, right? So I'm going to be writing down two equations. If this was a two-dimensional problem, I would be writing down a total of 4 equations. 2 for this and 2 for that. But this is a one-dimensional problem, so I can get away with only 2 equations. 1 for this and 1 for this. So let me write that down. Let me write down the set of equations so that now I have a place to start as I do my problem solving. So let's start out with one. So net force on mass 1. I add up all the forces in the positive direction, all the forces in the negative direction. That's the sum of all the forces. That should equal mass times acceleration. So what are my forces in the positive direction for mass 1? The way I define the positive. Right on the board. Yeah, m1g, not acceleration, but gravitational acceleration. Right? G is not acceleration. So, A is not a force. That's why I didn't draw it on the dot. Only the arrows I drew on the dot are the forces. I try to distinguish that so that I don't confuse myself. And hopefully once you know my convention, you won't be confused either. So the only 2 forces on this diagram are the tension and weight. So what's the expression for weight? Yeah?
So it's the force of gravity minus the tension.
Yeah, so m1g, that's the force in the positive direction, force of gravity. And this is the force in the negative direction, minus tension. So that's my total force, or expression for the total force. That should equal m1, mass of the object, times the acceleration. I guess it's the same, so yeah, acceleration. Okay? That's one equation. I need to write down equation for mass 2. So net force on mass 2 is equal to, so what are the forces in the positive direction? Tension, right? So tension. What are the forces in the negative direction? Yeah, gravity, m2g, it's in the opposite direction, so minus m2g. And that's equal to m2 times acceleration. And I should really take a little bit of time to explain my convention. So this is my set of equations. And the way I write down my equations, it has some conventions I like to use built in, which not everyone might be using. But I think it's a good convention, especially for introductory physics. So what I want you to pay attention to are these signs that I'm building into my equation. I could have actually written this differently. I could have said that net force on M1 is M1G plus T, and then say T is going to be negative. I could have said that, right? But by building these signs into the equation, the expectation I'm building is that when I go through all of this and solve everything, what I'm expecting is that T out to be positive. Okay? So that's the convention I'm following. That's why I'm being very careful to write down all the negative signs into my equations, because I'm building in that expectation into my set of equations. So when a variable happens, like T, happens not to be positive, that means something. Sometimes it's not a serious problem. Sometimes it means I was just assuming a direction of a force. It just happens to be in the other direction. Sometimes it means I was making an assumption for a problem that was not true, so now I have to go back and redo the whole problem. But what's important is that this is an expectation. This is my prediction. So if this is not true, then that's something I need to react to. I need to address, was that okay? If not, what do I do now? Okay? So, that's my convention, and I recommend that you follow it too. It'll help you spot any mistakes you make, any algebra mistakes you make, because you had an expectation for a value. If you get a negative answer, you did something wrong. So this is my system of equations. I have a system of 2 equations. I'm almost done. I'm almost ready to solve for acceleration. There's one last thing I like to do before I go off into trying to get an answer. What should I do? I've done it before in this class. Edward answered it last time. Someone else answered. What should I do before I go on ahead and try to solve for A?
Count the unknown.
Count the unknowns. I have to make sure that I can actually solve this. It's a question of knowing that it's doable versus venturing into unknown without knowing if it can be done. So if I count the unknowns, I have 2 equations. If I have exactly 2 unknowns, then I know it can be solved. Whatever happens from there, if I couldn't solve it, it's because something's wrong with me, not because something's wrong with the setup. So A is one of the unknowns. What are the other unknowns? Tension, yeah. T is the other unknown. So I have only 2 unknowns, so it should be solvable. Yeah. Okay, so I'm going to solve for this, and actually solving, that will be algebra practice. And this is one of the simpler algebras that you will need to for this class. So let me use this as a way to sort of guide you through that. All right. So I want to solve for A as my final answer. What should I do first? Like, what does your intuition about algebra tell you to do? Divide out M1. So what you're trying to do is you're trying to solve for A, right? I want to tell you to stop. Whatever quantity you want as your final answer, that's what you want to solve for finally at the very end. Because here's what you're doing. So you learned a lot of different algebra tricks in your math classes: linear combination, substitution, whatever, division. In this class, I'm going to stick to only one of those many tools: substitution. It's because substitution works almost always, and it might be more tedious, but it's a simple tool that works almost all the time. So when you're using substitution, this is the one rule I want you to follow. Always solve for the quantity you are trying to eliminate until the very last step. Now, is A what I'm trying to eliminate? No, it's what I'm trying to solve for. That means I don't want to solve for A. I want to solve for some other unknown. Here, there's only one other unknown, tension. So I'm going to solve for tension. So this is a little bit counterintuitive unless you've done a lot of system of equations type problem. So I'm going to solve for tension. Let me do, it doesn't matter which one I do it with. Let me do it with the first equation. So I'm going to solve for tension here. So move T over, move the other thing over. So I get T is equal to M1G minus M1A. Right? Now what I do is I'm going to use this to eliminate tension in the other equation. That's why I solve for tension. So combining this and this equation, plugging this into T, I get M1G minus M1A minus M2G is equal to M2A. So now finally I have one equation in terms of one unknown. So I'm going to collect like terms and solve for A. So let me collect the like terms. So I won't skip this step. So move M1A over to this side and then factor out A. So what I have is on the left-hand side, I have left to M1G minus M2G, M1G minus M2G. And on the right-hand side, I have M2 plus M1. So M2 plus M1 times acceleration. So the final step now is to divide out by M2 plus M1 to solve for A. So at the very last step is where you solve for the quantity you wanted all along. So acceleration is equal to M1G minus M2G over M2 plus M1, but same thing as M1 plus M2. And that is the answer that I wrote down at the very beginning, if you factor out G. So that answer is this answer. Okay? So let me go to problem 8, which will both serve as Newton's third law review and practice for using standard strategy in a relatively simple situation. So this is the setup. Well, there's a reason I had this up. This actually is the setup. I have two blocks which are in contact with each other. And since I'm going to be pushing it to the right, I'll just leave them magnetically connected together. So I'm pushing it to the right. Good? You see the motion? And this is a relatively simple motion. But here's the question that, philosophical question or academic question that we should address. Label this block 1, label this block 2. When I push, I'm touching block 1, right? Am I touching block 2? So how come block 2 accelerates to the right? Because I'm touching block 1. But okay, so my force is, oh, you mean the block 2 is touching block 1? Yeah. So block 1 must be applying force on block 2. All right, then the acceleration of block 2, is that something I'm getting for free? As in, however, like imagine I have some fixed amount of force, and whether this block 2 is there or not, with a fixed amount of force, the acceleration I get should be the same. Like your intuition says no, right? When this block 2 is here, it should take more effort for me to push. So how will that get reflected as I try to in my push? Block 1 still has one mass. Block 2 is not the mass I'm pushing. Yeah. So let's work through the standard strategy, and I'll highlight where the influence of block 2 comes in terms of, when there's more mass here, the acceleration should be smaller. That's your intuition. And we want to represent that in a rigorous mathematical way as well. Because what we are doing now is we are introducing a strategy that I'm claiming works for every single problem, even when you have zero intuition for the problem you're looking at. So so let's start with that. Let me draw the two blocks. I think. So this is worksheet 3, problem 8. So I have these two blocks, block M1 and M2. They are touching each other on a frictionless plane, and I'm applying a rightward force of F. And I'm not going to go, I guess I am going more or less in the order. So this is really the question I'm trying to answer. What is the acceleration of the blocks? Okay. So let's apply standard strategy. I mean, this is supposed to be the strategy we follow for every single problem. So to an extent, it doesn't matter what question I'm asking. Whatever question it is I'm asking, I probably need to go through this anyway. So let's start out with drawing free body diagram. That's the first step. So we are going to draw free body diagrams. How many free body diagrams do I need? Two. So I need one for block 1, another one for block 2. On block 1, what are the forces?
MG.
There's always gravity, mg. What other forces are there? Normal force. Here, by the way, these forces do nothing. They just balance each other out. They're not very interesting. But you know, we should draw them. Any other forces on block 1? Force that I'm pushing with. All right, that's good. Let me do that in purple. I'll draw uninteresting forces in black and interesting ones in purple. Any other forces on block 1? Frictionless. Stephen? Force of block 2 on block 1. Yes, there is such a force. For now, let's say, how many of you remember that there should be force on block 1 from block 2? Be honest. Really? All of you thought that? I only heard one person. All right. If you thought of it, great. And so if you are labeling it now, then sure, why not? You have, how should I label this? Let me label it N on 1 by 2. All right. Does this look now complete? Yeah, we identified everything that's touching block 1. The applied force, the block 2 that's touching block 1, normal force from the ground, and the rest is gravity. Okay, block 2, what are the forces? Gravity, M2G. And what other forces are there? Normal force, because it's not accelerating downward. So these are, once again, uninteresting forces if we won't do anything with it. Any other forces on block 2? So block 1 is touching block 2, so it's pushing it also. So I can call that normal force. It's pushing it to the right, right? So normal force on block 2 by block 1. All right. So as you look at this diagram, so we're still in step 1. Especially when there's more than one object in your system, this is a check that I would like to always do. This check is a check for Newton's third law. So we spent a fair amount of time on Newton's third law, and this is really where Newton's third law comes in. It doesn't come in any of these steps. It comes in the most important step as you're identifying all the forces. You should check for Newton's third law. As in, you should make sure the whole entire series of forces you have drawn is consistent with Newton's third law. What does that mean? What does it mean for all of this to be consistent with Newton's third law? So Newton's third law says that for an action force, there's a reaction force, right? So for every force that's here, I have to know where the reaction force is. The answer might be like for this gravity, where's the reaction force? Normal force is not the reaction force. How do I know these two are not action-reaction pairs? They are on the same object, so they cannot possibly be. Third law is the law of interaction. So how do you go about finding the reaction force? What's the first thing you should do? Opti first. Sorry, what? Okay, two objects that are interacting. So this object is one of them. Force is on one. Wait, is it two? Is two exerting this gravitational force? No. So you have to find the object that's exerting the gravitational force. I'm focusing on this. I'm focusing on this force. I'll get to all the other forces later. Right now, I'm focusing on the gravitational force. It is on M1. I need to find what's exerting, what's producing that force. the Earth. So for this force, that's the two pair of the objects interacting, the M1 and Earth. Now, Earth is outside my system. I don't care for the Earth. So I could draw the force on the Earth, but it's not in my system. So I'm going to identify this as an external force. It's a force that's exerted by an object that's outside my system. So if it's an external force, then we've finished our Newton's third law check, because the reaction force does not need to be drawn within our system here. Good? Let's keep going. Normal force. What's exerting the normal force? Table. Is this an external, or I guess the other version would be internal? Is this external force? Is table outside my system? Yes, my system is M1 and M2, that's it. So this is an external force. Once again, that means I don't need to identify the reaction force. It's going to be on the table, but I'm not drawing free body diagram for the table anyway. What about the applied force F? It's my hand. Is my hand in the system? No. Do you see a free body diagram for my hand? Yeah, if you don't see a free body diagram for the object, then unless you forgot an object, it means it's external. So all these are external forces. But you know, this is why so far we've been okay getting away with not doing the Newton's third law check, because many of the forces you see will be external forces. Because when you draw a free body diagram, you don't draw it for every single thing in the universe. You only draw it for the two things you care about, or three things you care about. What about the normal force on 1/2? This is internal, like it says it right here, right? By 2. So that means we need to find the reaction force paired to this force. Is that already in my set of diagrams? Yeah, it's this force here. So this is the step where if you had forgotten one of these forces, maybe you remembered this force, but you forgot this force. Then when you get to this point, that's where you should realize, wait, it's mass 1 that's exerting this force. There must be a reaction force. So this is the Newton's third law check. It's going through your diagrams all over again, making sure that where a reaction force is required, you have labeled it. And you will see this in the math too. This force is why the mass of this mass 2 matters. Because if I didn't have this mass at all, then for the free body diagram for mass 1, I wouldn't have this force. So this entire force will go into accelerating M1. But when mass 2 is there, when I have the mass 2 here, then now there's this normal force, the reaction force. So not all of my applied force goes into accelerating M1. It's that minus this that goes into accelerating M1. That's why when there's more mass here, it takes more effort to accelerate the whole thing by the same amount. Good? All right, let's finish it. This normal force and this gravity, are they internal or external? External, you know, reaction force is on the Earth, I don't care. Reaction force in the table, I also don't care. It's all on outside my system. So all these are external forces, but this is what it means to do the third law check. You either identify a force as being external force, so you don't have to worry about the reaction force pair, or it is internal, you do care about the reaction force pair, and you do find it, or you draw it if you forgot it the first time around. Okay? We'll look at other questions where it can get quite tricky. This, you know, once you realize this, then it's easy, but yeah. All right, so this is our free body diagram with all the complete set of features. Let me erase the extraneous label so that it doesn't get all cluttered. I mean, you know, you just to tell yourself that it's external force, you don't have to actually label it on the diagram. All right, so the question is asking to find, so whatever the question is asking, I should go through the rest of the steps because that's the whole point. This is something that I can apply for every single problem I see, every single force problem I see. So I need to define coordinate axis. Let me just define it in a natural sense here. I think I'm just going to define it like this. This is my positive x. This is my y. No reason to be funny about it. We'll do more about the coordinate axis when you get to 2D. That's where actually you have to be more careful anyway. All right, so step 2 is done. Step 3, so what breaking forces into component means is each of these forces, you look at it, which part of the force is along the x direction, which part of the force is along the y direction. Well, they're all either x or y, so I don't really need to do anything here. Good. So, all right, this is done automatically. And the final step is write down Newton's second law equations. And, oh, you know what, this time let me just write down all the equations that I can write down. And I will illustrate what I meant by these forces being uninteresting. So you have two objects, and you are writing down Newton's second law equations in 2D. What that means is you have to be writing down 4 equations total. 2 for mass 1, 2 for mass 2. So net force for mass 1 in the x direction, net force for mass 1 in the y direction, net force for mass 2 in the x direction, net force for mass 2 in the y direction. All right. What are the horizontal forces on mass 1? We're just copying it from the free body diagram. How many forces do you see? This is not a trick question.
The push
Apply the force, F, all right, plus F.
on 1/2.
Minus the normal force. Minus, and let me write it down as 1, 2. Is equal to, what should that equal to? Yeah, mass times acceleration. Technically, it's m1 times x component of the acceleration. But the point of defining coordinate axis so that it's along the direction of acceleration is that this just becomes the whole acceleration. I don't have to worry about x and y components. Okay, y components of the forces. There's gravity and normal force. So normal force is positive. So n1 minus m1g, that's equal to 0. So what this equation does is if you wanted to find the normal force, this lets you find it. And this will actually be useful once you start dealing with something called the friction. But until then, like, I don't actually care about what N1 is. Net force in object 2. How many horizontal forces are there? Yeah, the normal force. Let me call that N21, no other force. So M2, can I say it's the same acceleration? Yeah, same acceleration, they are moving together. All right, the last equation, it's vertical forces. So N2 minus M2G is equal to 0. Yeah. So this is kind of end of the standard strategy, which leaves you with this system of equations. 4 equations. And to make sure that you can solve it, you should count the number of unknowns. So let me count them. Acceleration, that's unknown, right? Normal force 1, 2, on 1 by 2, that's unknown, right? N1, is that unknown? This is where you have to be careful. Now, it's not unknown if you solve for it using the equation. So until you use this equation, it is still unknown. Does that make sense? Like, I know, so I mean, you guys can do this in your head. You can solve this for N1, get N1 is equal to M1G in your head. But yeah, but you know, until you do that, this is still unknown. Let me go through this and I'll explain what I mean. Okay, is N21 unknown? Normal force on object 2 by 1. Unknown, right? Okay. Acceleration, it's unknown, but I already identified it. I don't need to double count it. N2 is also unknown. So I have 1, 2, 3, 4 equations. How many unknowns do I have? I have 5. So I'm in a little bit of trouble here. Now, some of these are just overcomplicating the situation. Let me get rid of those right away. So those things that are overcomplicating the situation are this equation and this unknown. And this equation and this unknown. If you look through this carefully, N1 does not occur anywhere else in this system of equations except for this one. Right? Same thing with the N2. It doesn't occur anywhere else except for this one. So what that means is that you can use this equation to solve for N1. Say that N1 is equal to M1G. It's known. But at the same time, you got rid of one equation. So you're down to 3 equations and 4 unknowns. You can do the same thing here. You can use this equation to say n2 is equal to m2g. Good job. You got rid of one unknown, but you also got rid of one equation. So that's what I mean, these were uninteresting. It allows you to solve for normal force, but unless you wanted the normal force for some reason, like you haven't done yourself any good on net. So what you still have is 1, 2 equations and 1, 2, 3 unknowns. What can I do? So this is what I have to do. I have to either, this is a lot of times where you will be at the end of standard strategy. You will have written down Newton's second law equation, and if you are lucky, you will have exactly the same number of unknowns as your equations. But more often than not, you will find yourself in this situation where you have more unknowns than your equations. Then your goal is to essentially come up with more equations that's outside of Newton's second law. Maybe there are some quantities here that are related to each other that you didn't write down as being related. Do you see anything like that there? What do you see? Yeah, I like to pronounce it as N12 and N21. So yeah, N12 and N21 are related. How are they related? They are equal, and you know that because they are the action-reaction force pairs. So that's where you bring in the fact, oh, these are action-reaction force pairs. I know they are equal. I even marked them on the free body diagram. So that's where you realize, all right, N12 is equal to N21. And you already indicated their relative direction with this minus sign. So you don't have to do it twice. I'm saying their magnitudes are the same. So you might as well call this, let me just call this N, so that I simplify my notations. So this N12, N21, they're just the N. Then now I have only 2 unknowns. Acceleration and this normal force between the blocks. Good? Now this is solvable. Let me copy the cleaner version here. So the cleaner versions are F minus N is equal to M1A. And N is equal to M2A. This is the cleaned up versions of Newton's second law equations. Once you realize that these 2 forces are equal to each other by Newton's third law. And this is, by the way, how you should be using Newton's third law. This is, in fact, the way it's mistaught in high school physics or whatever. You focus so much on equal and opposite, you go to the right away. You find the 2 forces that look like they're equal in magnitude and say they are action-reaction pairs, like gravity and normal force. That's exactly backward. The way it goes is you identify 2 forces as action-reaction pairs, and from Newton's third law, then you know that these must be equal, because that's what Newton's third law says. So you don't start out with the 2 forces being equal in magnitude. That's the conclusion you reach at the end. And that helps you solve this problem. Right, so let's finish that. It's not too much work from here. 2 unknowns. It looks like N is already solved for. So let me plug this into here to solve for acceleration. So when I plug it in, what I get is F minus M2A is equal to M1A. Move this over, factor out A, divide that by M1 plus M2. Then you get acceleration is equal to F divided by M1 plus M2. Is this the answer you would have guessed? If somebody just told you, this block has mass M1, this block has mass M2, I'm applying a force F to both of them. What's the acceleration? Would you have guessed this? Right? Force divided by total mass. Yeah, this is, I'm using this problem as an example because this is not a difficult question. And you can answer now that we have done all this, you can actually answer part C also. By plugging this acceleration back in here, you can find the magnitude of the normal force. Assume everyone can do that. So this is once again an example of applying the standard strategy. It's simple enough that you can use your intuition to check if this answer makes sense. And what I keep telling you is that, so like for this problem, why did they even use this? It's like, I don't know, using a hammer to kill a mosquito. The point isn't to kill the mosquito. Point is to learn how to use the hammer. Point is to learn how to use this tool. And are actually going to apply this to more difficult problems that's going to need you to know how to exactly apply this. Okay? All right. I think we might be able to do problem 13 very quickly, maybe. Every semester I skip it, but I don't want to skip it this semester. So let me give this problem to you. Let me give you a few minutes to work through this and see if you can get the answer. So, you can answer the whole question, but this is really all I want you to answer. So this is the picture here. Someone's in a bucket, and she's pulling on a rope which goes over a pulley and is attached to the bucket. And the question is this: how hard must she pull to raise herself at constant speed? Or in other words, acceleration equal to 0. How hard does she have to pull so that she doesn't accelerate? She said, she doesn't accelerate. So try going through this. Draw a free body diagram. Label all the forces that's on the bucket and the body, and try going through this and see what you get. All right, ready or not, we are going to start out with the free body diagram. So we'll talk through it to see what forces are on body plus bucket. I'm just going to call it body. The bucket's name's body too, and we'll figure it out. So this is body. What are the forces on bodies? There's always gravity, so mg. Any other forces on body? There's tension. How many tension forces should I draw? 2. Because the string is actually contacting bodies at 2 different points. There's the place where body 1 is holding onto the rope, and there's the place where the rope is held to the body 2. Okay? So there's actually 2 different tension forces. One that's pulling up from where she's holding onto by hand, T1, and one there, the string is attached to the bucket, so T2. Are these 2 actually the same magnitude of tension? You have the intuition that they are. It's over a pulley, frictionless, all that stuff. So they're actually the same tension force. Yeah?
Why don't we assume that tension's on the bucket, not on body?
Oh, well, sorry. When I say body, quote unquote body, I really mean body plus bucket. So I'm treating the 2 as one system. So, yes, it's pulling on the bucket. Bucket's going to be pushing up on body through normal force. Body's pushing down on the bucket through normal force. So when I treat this as one system, I'm ignoring any internal forces between them. So, when I move this cart by one end, there's actually a lot of complicated forces internally. And we are going to get to some of that when we get to rotation. But for now, I'm just ignoring all those internal forces. Just say whatever force I'm applying is on this one point object. I'm doing the same thing here.
So this system only has one mass.
One mass, yeah. That's the combined mass of 75 kilograms that they have given you, which I'm not actually going to plug in. That good? Okay. So that's the free body diagram. It asked for how hard must she pull. So I guess what they are really asking for is this tension force here. But it almost doesn't matter whatever is it they're asking. We are still going to go through these steps. We drew a free body diagram. Check for third law. It's one object, so third law is automatically satisfied. Define coordinate axis. All right, I guess I need to do it. Let's say upward is positive. Doesn't really matter because it's not accelerating. Break forces into components. They're all vertical. I don't need to break down anything. Step 4, write down the Newton's second law equation. So what I'm writing down is the net force, which is upward tension forces, T plus T minus the downward gravitational force, mg, is equal to, what should that equal to? 0. Mass times acceleration, but we know acceleration is 0. So might as well say it's 0. Makes things easier for us. So what is t when you solve for t? 2t is equal to mg, so t is equal to?
mg over 2.
Yeah, mg over 2. So she doesn't have to pull her entire weight. She only needs to pull half of her weight. This is, by the way, example of what's called, oops, typo. This is what's called example of a simple machine. That's the title, simple machine. And what the simple machine does is so daddy can support her entire weight using only half the force, or half the output force. So simple machine is an arrangement that multiplies how much force you're applying. Anybody here have seen other simple machines in life? Anybody here use crowbar other than to smash people? Okay, has anyone here used a crowbar? Yeah, what is a crowbar an example of? Lever, right? So you have a pivot, and when you do lever like this, you can apply small force to get a lot of big force. So we're going to see more example of that, but this is one of the first examples that we can already see based on our understanding of forces, how pulleys work, and all that stuff. Yeah? So it's a simple example. So what I want to do instead is go through an example problem as a way of illustrating how you use this standard strategy to answer some non-trivial question. So here's a situation that you guys actually saw in lab. And in the lab, I just told you that you will learn how to derive this formula. But the formula you were given dealt with when you had an inclined plane. And what is the acceleration of this, given the angle of the incline and the gravitational acceleration? Anybody remember the formula? No? Let me draw the picture. While I'm drawing the picture, tell me if you remember the formula. So this is angle theta, and you have a mass on a frictionless plane. And the answer, the formula you might remember, is that acceleration is equal to g sine theta. Somehow, regardless of whatever the mass this is. So this is a good opportunity for me to point out what the point of this class is and what the point is not. If you have this memorized, great. Having it memorized will help you check what your answer is. If you don't have it memorized, don't worry about it, because the question actually is what is the acceleration? And if you simply write down g sine theta, that's an answer that's going to get at most 3 out of 5. 2 out of 5 if I'm pissed at you. Well, at most 3 out of 5, because the point of this class is that you should be able to derive that formula. So that's the goal in physics class. I know in most of your other science classes, that wasn't what you're asked to do. Most of your other science classes, you are given the formula and you are asked to apply it. We physicists, we think application is easy. Applying known formula, that's way too easy. Anybody can plug numbers into calculator. So what we want to do is we want to be the ones deriving the formula. Yep. And that's what these steps are meant to guide you towards that. So let's go through these steps and derive the formula for what the acceleration is. So what's the first step? Draw free body diagram. So that has a bunch of implications, but the first thing is you have to draw a free body diagram. So I have this mass here, all right. That's my only mass in my system. I don't care about the ramp. What are the forces? There's always gravity. Good to know. It's straight downward, right? Okay. Any other forces? Normal force straight upward? No, because this, remember, normal means perpendicular. So it's perpendicular to the surface it's touching. So this is probably a point where it's helpful for me to draw a few auxiliary figures. So this is the incline of the plane. And what I'm going to end up saying is, all right, the normal force is going to be perpendicular to this plane. Yep. Any other forces? Well, we said frictionless. Yeah. Any other forces? The thing that might be a little bit confusing is that when you have this cart, does it go straight downward? Does it go perpendicular away from the cart track? No, it goes along the track, right? And that's the complication you get in 2D because you have these two vector quantities. They are not exactly opposing each other. So when you add these two together, their sum can be pointing in some other direction. The rest of the steps will guide us through that. But you have a sense of what direction the acceleration is. You have a sense that acceleration points down the hill. Good? That I'm pointing this out because I'm moving on to step. So I'm pretty sure this is completely free body diagram. So I'm moving on to step number 2, defining coordinate axis. So how should I define my coordinate axis? Regular straight axis or tilted along the plane? Tilted along the plane. So that's advice or a rule that I would give you that's applicable in 95, 99% of the problems. Choose your x-axis so that it's parallel to the acceleration. I will explain the reason as I'm moving on to step number 4 eventually. But this is an advice that would be good for almost any case. And I want you to pay attention to, you want it parallel to acceleration, not any planes. Acceleration is the direction that matters. So here, I'm going to pick, all right, this is my x-axis, and this time how I draw y might matter, y. Okay. All right, I define my coordinate axis. Now I'm doing step number 3, and this time it's non-trivial. As in, I actually have to break down some forces into components. Do I need to break down normal force into components? Yes. Look at it carefully. Is it in any direction other than y? No, so I don't need to. Now I should recognize that it only has y component, but that's it. The entire thing you see is the y component of normal force. What about gravity? Yeah, I have to. Oh, by the way, I want to remind you of a convention that I use when I speak in this class. I use the word x and y to refer to the relative to the axis that we defined. If I want to talk about horizontal or vertical, then I will say horizontal or vertical. So it is true, gravity is entirely vertical, but it's not entirely in the y direction. Does that distinction make sense? Yeah, I try to be very careful with the language here. So, all right, so I can sort of pictorially represent how this will be broken down into sum of 2 different vectors. I draw a right triangle. So here's a vector that goes only along the y direction. Here's another vector that goes only along the x direction. And the way they are drawn, this is a right angle here. So this is what you might call the y component of the gravity. This is the x component of gravity. And in step number 3, you could leave it like this. But I actually like to write down what these are in terms of given quantities. In terms of, for example, given theta here. So this is where I need to do a little bit of geometry exercise to try to express these 2 components in terms of theta and probably mg, the hypotenuse of the right triangle. So let me ask you a trick question. Well, trick for some people. What do you think x component of this vector is? Yeah, it's a trick question because I knew at least one of you will answer mg cosine theta. You'll find that it's not. Yeah. So I really recommend everyone to go through these set of steps that we are going to go through right now. Because if you have this automatic association of x with cosine and y with sine, which is understandable, that's what you saw in trigonometry. The way things are drawn in physics classes, sometimes you will see them flipped. And there's no hard and fast rule that will tell you which is what, other than going through this geometry exercise that we are going to go through now. Okay? So this is what I'm going to do. I'm going to draw some more auxiliary figures to help me identify all the angles. That's what you do in geometry, draw auxiliary figures. So let me draw the horizontal line. What that lets me do is that lets me label the given angle theta. That's the very first thing you do. You have to know given angle theta. You have to know how that would be represented here. Then the next thing you do is you have to go through the geometry exercise to identify this theta with either this or this. It's going to be one or the other, but I had to figure out which it is. Yeah? So before going through all this exercise, how many think this theta is equal to this angle here? How many think it's equal to this angle here? All right, let's go through the exercise. So, this is something you have to get practice in. When you get practice, you'll be good at it. But until then, you're guessing right now. So this is how I do it. So I identify some of the right angles that's going to be helpful to me. So I know this is a right angle, right? And I know this is a right angle. It's two different sets of, perpendicular axes. That's going to be useful to me, so I'll keep that in mind. I think the quickest way to get to one of these two angles is to say this is also theta. Everyone sees that? Yeah, it's the other side of the theta that I labeled. So what I can say is that this angle here is 90 degrees minus theta. Everyone okay with that? All right. Comparing this angle combined with this angle, what angle do they add up to? Does it look like they add up to 90 degrees? Right? This whole thing is a line. This is 90 degrees. So this is 90 degrees also. Good? Which means that this angle, I can call this 90 degrees minus 90 degrees minus theta. What is that equal to? Theta. So if you guessed that this angle here is theta, you guessed correctly. If you didn't, I say guess, but some of you might have actually known that for a fact. But so this is a geometry exercise that you're going to get plenty of practice working on homework and whatever, and you're going to get good at it, and you kind of have to get good at it. Otherwise, oftentimes you're just guessing, is it cosine or sine? Is it cosine or sine? And half your guesses will be right, and half your guesses will be wrong, and you don't really want that. You want to be right 100% of the time. So having identified this angle as theta, the rest of our job is a little bit easier. Now we can say, all right, we know the right triangle, we know which angle is theta. So now hopefully all of you will be right when I ask for how is this leg expressed in terms of the hypotenuse and the angle. Is it mg sine theta or cosine theta? Sine, it's the opposite side, right? So this is actually mg sine theta. And this is really why this particular example is so confusing, because we call this x component, but it's sine theta, not cosine theta. So the y component should be mg cosine theta. It's the adjacent side. Good? So, the first few times you do it, step number 3 is going to take a little bit of time, because you have to go through this geometry exercise to figure out this angle. Well, that's the most time-consuming part. Once you have that, then the rest should be easier. Good? And having this will help. Because, the next step is step number 4, writing down Newton's second law equation. And knowing the x components and y components separately right away will help you just copy the information over to the set of equations you are going to write down. Okay, how many equations do I need to write down for Newton's second law? Is 1 enough? 2, why 2? Somebody said 2 from this side. Yeah, I need 1 for each component, so 1 for x, 1 for y. So I need a net force in the x direction, net force in the y direction. All right, tell me all the forces that are in the x direction, or the components of forces that are in the x direction. The x component of gravity. So that's going to be mg sine theta. What is that equal to? Yeah, now in general, it'll be this. It'll be mass times x component of acceleration, right? That's what it is in general. Let me do the y component, and then I will explain why we have this recommendation if you didn't already figure it out. Net force in the y direction. What are the forces with the components in the y direction? Normal force, the whole thing is. And any other forces? The y component. It's opposed, so it's minus, as you're saying, minus mg cosine theta is equal to, what should that equal to? Some of you might have that intuition already, that it should be equal to 0. Now, technically, what it is supposed to be is mass times y component of acceleration. Now, what is the y component of acceleration in our case? 0. And that's by design. Because we chose our axis so that x-axis is along the direction of acceleration, that made y component of acceleration 0. That is really why this recommendation is there. So now I can say this is equal to 0. It makes your equations simpler. Now, if you had chosen this other axis, ignoring my advice, that doesn't mean you couldn't do the problem. It means that when you do the problem, you will actually have to write this out, ax and ay, and you'll have to, work out the components of acceleration. In this class, we will always define our coordinate axis this way. So, we will never define our coordinate axis this way unless somebody forces us to, so that we will always have this situation here. The x component will be mass times the acceleration. Or, it can be flipped around. The x component can be 0 and y component is the simple one. And the other component will choose our coordinate axis to make this happen. Okay? All right, so that's it. This is the end of the standard strategy. This is the first time we are doing it in the full two-dimensional case, so it took quite a while. But the point of your practicing it in your homework and in your homework is that you'll get faster. All right, what do we do now? We are done with the standard strategy. You have no more guidance. So what do you do now? Yeah? We count the unknowns. What's the goal? What's the goal we are trying to get at? Find the acceleration there. Find the acceleration. So yeah, so we are trying to solve for this acceleration here. So as Joseph was saying, we count the unknowns. We count the equations, 1 and 2. And as this is same as before. We count the unknowns and we hope that there's no more than 2 unknowns. Or you should hope there's exactly 2 unknowns. So acceleration is unknown. Any other unknowns? There's one more unknown. Yeah, normal force. Normal force is not known. Until we solve for it, we don't know what it is. Yeah, we don't need it though. So if you wanted to say, all right, this is my system of equation. I have one equation and one unknown, that would actually be fine for part C. But then in part D is where you need to find the apparent weight and you need to bring in the second equation eventually. Yeah. So okay, so we can solve equation 1 for A. Well, divide out M. That's where you get A is equal to G sine theta. And this is the derivation of the formula that you have seen in class or seen in lab. And if we solve for N, the normal force, or what they are calling apparent weight, will be equal to mg cosine theta. So this is the simplest, non-trivial 2D force question that we can give you. It's non-trivial. It involves 2 forces, more than 1 force, and they are at some angle to each other, so it's a non-trivial 2D question. So, working through this, try working through this again on your own after class, and I'm hoping that will help you understand the procedure. Let me actually do just problem 3. That's another non-trivial question that I could ask. It actually should look familiar at some level. This problem 3. Well, let me have you look at it. Does it look, in some sense, familiar? You haven't seen this exact question, but you have seen a similar question. All right. What similar question have you seen that kind of looks like this one? The lab, right? The dynamics lab. In fact, if you took this result, or took this situation, said that theta is equal to 0, that's exactly your situation. Okay? Or if you take this, make theta equal to 90 degrees, that's the other Atwood's machine question that we did before lab on Tuesday. So this is a sort of, think of this as a more general version of the situation you have seen. And with all the tools we are introducing for these, now we have tools to answer this very general question. So let's give it a crack. So let me draw the figure. Incline the plane. mass, how did I, is the one on the plane M1 or M2? I can't read from here. M2, okay. I have pulley here, and this is M1. All right, and what they are asking you for, it almost doesn't really matter, but you know, since they are asking for acceleration. Do you know the direction of acceleration? Not really. Even if they told you the masses of the masses, you wouldn't really have a sense right away what direction acceleration is, right? Is it acceleration down the hill or is it acceleration up the hill? I don't know. Let me give you an advice. In many of the questions where you don't know the direction of the quantity that you are being asked for, take a guess. That's what I did here. I took a guess. That's down the hill. And when you go through the whole question with this as the guess, sometimes there will be something you can watch out for that will tell you if this guess was right or not. Good. So right now I'm just taking a guess. All right, I'm going to say acceleration is down the hill. Okay, what do I do to try to answer this question? Or really any other question? Yeah. We start out with a free body diagram. And I really want to emphasize this, that we call this a standard strategy because no matter what the question is, if it involves forces, this is where you start. You know, at some point, I hope this is almost a mechanical step, except for step number 1, because that's where you have to do a lot of thinking. So let's draw free body diagrams. How many do I need? 2. All right, 2 is fine. You could go with 3, but 2 is fine. Most people draw only 2, M1 and M2. If I drew the third one, any ideas what the third one should be? Pulley or the ramp, yeah. That's another object you could identify, but I'll just decide, all right, 2 is enough. Pulley is not moving anyway. All right, let's start out with the M1. What are the forces on M1? Gravity, always. Always a good guess. Be the first one to answer, and that can be your answer. What are the other forces on the hanging mass? Tension. The tension, yeah. Same as what you saw in the lab. Any other forces? It's not touching anything else. That's it. What are the forces on M2? Gravity, always. So Ali, any other forces on M2?
Force tension.
I was asking Ali. All right, tension. Do you know any other force that's not tension? Do you guys listen? Normal force, never mind. I was asking a specific person. Okay, Ali, are these directions I've drawn correct? Okay, good. All right, so you know, at this point I should really start drawing some of the auxiliary figures, because what I should say is the tension is along the same direction of the direction as the direction of the plane. So I should really draw some of the auxiliary figures, say that this is the angle theta that they've given us, and then you know, normal force is perpendicular to this plane. Let's see. Oh, is this a completely free body diagram? Did we forget any forces here? Okay, good. Oh, and I guess I've just labeled these 2 with the same symbol. Is that correct? Are they the same force? Like, what would you look for to make sure that this was correct? That tension here and tension here are the same. There's 2 conditions that many of the problems, textbook problems will say. Sometimes I will forget to say it in my questions, as I have, no, I didn't forget it here. There's 2 words that you are looking for that justifies this. Massless and frictionless. So this. Massless, oops, missing an S, frictionless. So that's what justifies these 2 being the same. And until we get to rotation, about month or 2 from now, that will always be the case. Okay? So, all right. So we are done with the step number 1. So wait, we're not done yet. We are almost done, except because I have 2 bodies, now I should for Newton's third law. Okay? This should be a habit that you always check for Newton's third law. So with this check, what we are doing is we are making sure that every one of the forces we have drawn, either they are external force or It's an internal force, and here's where the reaction force is. So the gravity, is this external or internal? External, it's coming from the Earth. The tension force, is it external or internal? This is a tricky one. So what is providing this tension force? What object? You might say string, but like, string we are treating it as massless. Let's say you don't want to attribute to the string. You could have attributed to this segment to the string, but you didn't want to. So you keep following the string. And where would you have to say on this object now is the reaction force? Now, if you do that, then you realize you are in a bit of a trouble. These two forces are not exactly opposite to each other. So they are not action-reaction force pairs.
They're the same force.
They're same magnitude, but they are not opposite direction. The third law pair, the reaction force, has to be pointed downward. So on what object here is the downward tension force? It's on the pulley. That's why I kind of want you to draw the force, free body diagram of the pulley. If I did, on the free body diagram of the pulley, there I would have reaction force to that. And here I would have reaction force to that, pulling it that way. But the pulley gets complicated. It's attached to the ramp, it's attached to the ground. So there's going to be some other force of the ground that's going to keep the net force at 0. Which is why if you didn't want to draw it, that's fine. It doesn't add anything. So here, for the purpose of our current discussion, we can say tension is an external force. That's just the code word saying the reaction force is on the pulley, and pulley is not in my system. Everyone okay with that? All right, let's keep going. What about this tension? Oh, we just talked about it, right? External. What about the normal force? External. What about gravity? Also external. Yeah, that's it. They are all external forces. So in this particular problem, if you forgot to do the third law check, you wouldn't have missed anything, only because you got lucky. So even when this check doesn't matter, it's good to have a habit of always doing the third law check, because there are some problems where it matters. Okay. This is the very last thing I do in step number 1. Now I'm done with the step number 1. So I need to define my coordinate axis. Is there one axis that will work for both objects? Yeah, once you start looking at the acceleration, so this is my assumed direction of acceleration. So that means this must be accelerating upward. They're not in the same direction. What that means is no one axis will work for both of them. So can I define two different axes? Yeah, I can define it, one for this free body diagram, one for this free body diagram. There's nothing stopping me from doing that. So let me say, this one is essentially a one-dimensional problem, right? So let me just make it one-dimensional. I'll say this is my positive direction. This is now a two-dimensional problem. So I have to say the direction along the acceleration, this is my x. And the direction perpendicular to the acceleration, this is my y. Everyone okay with this coordinate axis? All right, now we move on to step number 3, breaking forces into components. Let me actually have you do this on your own. So these don't need to be broken down into components. It's only gravity that needs to be broken down into two components, y component and the x component. And you could look up the answer that we just did before, but let me give you a minute or two to go through the whole algebraic argument again. This time maybe using the angle theta that's drawn here. Everyone done? We're still working through? I'm kind of running out of time. So the thing with the geometry is that there are many different ways to do it. So the way I'm doing now doesn't have to be the way you did it. But the point is you should be drawing auxiliary figures and identifying the angles you need to identify. So I'm starting out with this theta. I want to identify either this or this as theta. So what I'm going to do this time is I'm going to use this right triangle that I see in my mind's eye or whatever. So it's a right triangle with this being the right angle. So this angle must be 90 degrees minus theta, which means since this whole thing is right angle, this must be theta. It's the answer most of you knew already. It's the exact same thing we did last time, except this time I went a little bit different way. So this will take practice. Practice it on homework, and on an exam, you don't want to be spending too much time doing this. But it does need to be done. Okay, so with this, I can say this is m2g sine theta. This is m2g cosine theta. I have broken all the forces into components. Now I'm finally ready to do step number 4. And everything that we have done is to let us to step number 4 easily, quickly, just by copying information from the free body diagram into equations. If you've done everything correctly here, this should be an easy mechanical step. Yeah. Okay, how many equations do I need? More than 2. I have 2 objects. How many equations do I need for this? 1. How many do I need for this? 2. So 3 total, yeah. So I need a net force on 1. I need a net force on block 2 in the x direction. Net force on block 2 in the y direction. So let me go through this quickly. Net force on 1, that's going to be tension minus m1g. What is that equal to?
0.
Not 0. It's accelerating. m1a, right? Yeah, the Newton's second law, mass times acceleration. So it's the mass of the object times the acceleration. And everyone's okay with these two having the same magnitude of acceleration, right? They move together. So block 2, along the x direction, you have tension, which is going in the negative direction. And you have the x component of gravity, which is going in the positive direction. So I'm going to write down m2g sine theta minus t is equal to m2a. And this is by design. We chose our coordinate axis so that this acceleration, instead of being just the x component, it's the whole thing. Or the x component is the whole acceleration. The y component, I have normal force and gravity. So n minus m2g cosine theta. Now this is equal to 0, and by design. We chose our coordinate axis so that there is no component of acceleration along y. We chose it that way. So this is 0. Okay? So this is our system of equations that falls out of applying the standard strategy. And what I'm trying to impress on you is that up until this point, there is a fixed set of steps you can follow. So after you've done free body diagram, which takes a lot of decision-making process, once you've done that, the rest are just your math skill. How well do you remember geometry, and how well can you copy? And so, but this strategy doesn't solve the problem for you. It leaves you here with a system of equations. And from here, it's now up to you to finish the problem. So the question asks you for acceleration, right? So let's solve for acceleration. Does it also? Yeah, it asks, let's solve for tension. We should solve for tension. So let's solve for acceleration and tension. And this time, I'm just going to do the algebra myself because I'm running out of time. So let me just start out with the simple check that we always do. I have 1, 2, 3 equations. I have 1, acceleration, 2, tension, and 3, normal force that are unknown. And staring at this for a while, I'm going to decide, after looking at that and realizing that it's not asking for normal force, I'm going to decide to ignore this. Because this is yet another situation where I have one more equation that has one more unknown that's not used anywhere else. So I'm going to ignore this for now. Once we introduce friction, I will actually stop doing that. Because once we introduce friction, this will become necessary. Okay? So I'm going to solve this system of 2 equations with the 2 unknowns instead. Makes things easier for me. So do I want to solve for acceleration first or tension first? It doesn't actually matter because they are asking you for both acceleration, and tension, right? So let me do the unusual thing and solve for acceleration first. It's not the usual thing to do, but there's nothing wrong with the unusual thing. So let me solve equation 1 for acceleration. So that says acceleration is equal to t divided by m1 minus this divided by m1, so just to g. So that's it. Now this is not answer for acceleration, of course, because it has t, an unknown. You have to plug this into the second equation to eliminate acceleration from your set of equations and solve for tension. So plugging this, combining these two equations, you get m2g sine theta minus tension, I haven't eliminated tension, is equal to m2 times the acceleration. So that's a t over m1 minus g. All right, I'm going to collect like terms together. Like terms meaning terms containing t and terms not containing t. So I'll collect all the terms containing t on the right-hand side, everything not containing t on the left-hand side. So on the left-hand side, I end up with m2g sine theta, and then m2g moved over, so it's a plus. Wait, plus? That sounds fine. M2g, so M2g. And then I move this over to the other side. And I'm going to factor out t from both of them. So it's going to look like 1 plus M2 over M1 times t. Everyone good? Yes? OK, so to solve for t, I divide the top of both sides by this expression here. So when I solve for t, I end up with t is equal to this whole thing. There's a lot of m2s there, but I don't think there's anything. Wait, did I miscopy something? No, seems right. Oh, I know what it is. Yeah, it's fine. So m2g sine theta plus m2g divided by 1 plus m2 over m1. When you stare at this, it might make you think, well, I don't know. Anyone have problem with this expression? Does this not look like a right answer? If you don't, that's fine. I'm pretty sure this is correct answer. So believing this to be correct answer, let me plug it into expression for A to solve for acceleration. Okay? So combining both of these together, let me use, what color haven't I used? The blue. Combining this equation and this, so I say acceleration is equal to that whole thing over m1, m2g sine theta plus m2g over m1. So I'm multiplying by 1 over m1. So this 1 is going to turn into m1 plus, that's going to cancel this, so m2. I'm not done. I have to subtract minus g. Minus g. All right, that's my acceleration. Does it look complicated? Does it not look complicated?
You can take the m2z common and then
Yeah. So what I want to tell you is that if you wrote this as final answer, the way I grade in this class, this is correct answer. So, you know, a lot of people have phobia with algebra. And one guarantee that I want to give to you is that if you leave this here, I won't mark it as incorrect. This is correct. Now, it is complicated. If you can, you do want to simplify it. And I do want to encourage you, all of you to try simplifying it. But, you know, if you left it this as the answer, it's not wrong. It's not wrong. But it can be simplified. So let me try simplifying it a little bit. 1, I see that I can factor out g, so let me factor out g. So what I end up with after factoring out g is this. Equal to g times m2 sine theta plus m2 over m1 plus m2 minus 1. How would I simplify this? I can combine fractions. This is one of the techniques. When you have a number like 1, you can express it in different forms. One other form to express this 1 is as 1 plus m2, both on the numerator and the denominator. The point is now I have the same denominator. So I can add these two together. When I do, you see that this minus m2 cancels out this m2. Right? Yes? Yeah, so you end up with the whole thing is equal to g times this thing, m2 sine theta minus m1 divided by m1 plus m2. And this is as simple as it's going to get because it's on an incline and whatever. And depending on the values of theta, it can be simpler. If theta is equal to 0, then you get the situation that was same as your lab. And if theta is equal to 90 degrees, you get the Atwood machine. So I want to circle back to one choice that I made earlier, very early in the problem. This choice here, that acceleration points down the hill. Is this always going to be true? Intuitively, you know that this is not always going to be true. So what in our solution can we point to and say that whenever this condition holds, we can say that acceleration does not point downward? Do you see anything in our final answer here?
M1 is greater than M2.
Not M2. It's close, but there's one more thing you have to consider. So this is the part of the solution I want you to pay attention to, the numerator. That's where you have two differences. This is the only part of the solution that can become negative. Right? And it becomes negative when m1 is greater than not just m2, but m2 sine theta. This is the part that made trying to guess this initially complicated. So when this happens, this is negative. So what do you think it means for this to be negative? Yeah, it accelerates the other way. So the m1 accelerates downward, and m2 accelerates upward. So here, if you were wrong about the direction of acceleration, the fix is simple. You just say, oh, the negative acceleration, it means it's the same magnitude of acceleration, it's just the other way. So this is a lot of the problems are like this. There are some problems where you do have to be aware of where negative answer means it's something different entirely. Actually, that deals with the friction, which, sorry, I ran out of time for. Yeah, I ran out of time for.
So what I thought I would do is illustrate how the steps that we recommend compare with the two written materials you have for this class. Your textbook, the OpenStax University Physics, and the portable TA. And I will make a comparison so that you can see how what we are recommending here lines up with what you see in those other materials. So drawing free body diagram itself will take some practice. And once you do that, then you have these steps laid out. Step number 2, step number 3. And by the time you get to step number 4, really all you have to do is read off information that's already in the diagram. So let me give you a bit of a comparison between how we give you these 4 steps and how the textbook and the portable TA lays it out. This is the set of steps that are in your textbook. So your textbook doesn't give you really a single reference for Newton's law strategy, but let me just link up those things that are both in the textbook and in what we give you so that you can see the connections. So in your textbook, what we lay out as a standard strategy is broken out in two sections. One is in chapter 5.7, drawing free body diagrams. And in chapter 5, there are some questions where you could use detailed force problem solving strategy, but much of that has been reserved for chapter 6, applications of Newton's laws. So in that organization of the textbook, the whole layout of this strategy kind of gets broken up into two pieces, which I think is a little bit unfortunate. So the first part is in section 5.7, and it's in problem solving strategy, constructing or drawing free body diagrams. So this is what your textbook says, and let me just draw the comparison. So in your textbook, it tells you draw the object under consideration, and it does say if you are treating the object as a particle, represent the object as a point. And that's what you are seeing us do so far in this class. And step number 2 here says, include all the forces that act on the object, representing these forces as vectors. And these two steps that are outlined here correspond to our step number 1, drawing free body diagram. And it's kind of difficult to describe all the things that should be going on in writing. So that's why you have a few videos, including the videos from last week that illustrate the process for drawing free body diagram. And what we give you as step number 2, it might look like in your textbook, there's no step number 2. This is something that we are kind of pulling out from a step that is given in the textbook. So the textbook says, convert the free body diagram into a more detailed diagram showing the X and Y components, which corresponds to our step number 3, break down forces into their components. Now, here's something that the textbook presumes that you have. X and Y components. You can't really talk about components until you have the axis. Now, if you're always dealing with a straight axis, then it's obvious what the X and Y directions are. But very commonly, especially in this class, you will have situations where it's more convenient to use axes that are tilted. That's the reason we break out step number 2, so that we are encouraging you to give some thought to how you choose your X and Y axis. So that's step number 3. And I guess what they're telling you in this step number 4, if there are 2 or more objects, draw separate free body diagram for each object. That feels like that's something you should have right at the beginning when you are actually drawing the free body diagram. But anyways, so we just put them in the right order so that you start thinking about drawing the free body diagram for each object from the very first step instead of checking to see if you did it wrong after you've done it. So the one step that your textbook leaves out is the step number 4. And that's a kind of a consequence of how the textbook breaks out these problem-solving strategy into 2 sections, one in chapter 5 and one in chapter 6. So in chapter 6, they give you what they call problem-solving strategy, applying Newton's laws of motion. And some of the steps that they are laying out here is a bit duplicative, because these first 3 steps here, this is drawing free body diagram, as they already covered in section 5.7. So really the only new thing that they are introducing here is what they are saying, apply Newton's second law to solve the problem. And our application of Newton's second law is writing down this equation. And the idea is that if you have followed these steps, which is, I guess, kind of, well, it doesn't match number for number, but it is our steps 1 through 3. If you have done that, then all the information you need to write down Newton's second law for equation for each object, it should already all be in the diagram. All you are doing is this step now is simply reading off the information. So yeah, so that's how it matches up with the textbook strategy. Now, there's something we kind of omit in standard strategy. In particular, so in your textbook, it says, if necessary, apply appropriate kinematic equations from the chapter on motion along a straight line. And it says something about the check the solution to see whether it's reasonable. And all that's good. I don't include them as part of standard strategy, because I guess what I want to impress on you is that this doesn't actually solve the problem for you. It sets you up to solve the problem. Because once you have written down Newton's second law equations, then what you have left is a system of equations on which you can do the algebra to try to solve for the unknowns. And sometimes, depending on the problem, you might have to bring in additional information, like the kinematics equations, to have enough number of equations for the number of unknowns you have, and solve that. So really, there's a step number 5, which is actually solving the problem. But once you get to step number 4 and you have system of equations, then most of you know how to go from there and solve your system of equations to actually get a result. And checking to see whether solution is reasonable, that's a habit you should be building, and we'll be illustrating that plenty of times throughout this semester. Okay, so that's it, how it matches up with the textbook. Let me show you the example from the portable TA to show you how it matches up with what you will see in portable TA. Question 9.2. It'll say, let me reiterate the strategy introduced in question 8.6. So let's go back to question 8.6 and look at what the strategy introduced is. I'm actually hoping that you have been reading through the portable TA as you are working through homework questions, so that you have actually seen it. So this is question 8.6. And it actually deals with a situation that's quite a bit similar to the question that you are dealing with in your lab, with a bit of a special modification in that the theta is equal to 0 for the situation in the lab. But otherwise, it's dealing with the 2 blocks connected by string, so it's quite similar. So, so as it says, this is a classic multi-block problem. And in the answer, Andrew Elby introduces what he calls multi-block strategy. This is what he introduces. He says, draw a free body diagram for each mass individually. So what he calls step number 1 here, that matches up with our step number 1, draw a free body diagram individually for each object. And then if you just read step number 2, it kind of looks like he skipped right up to step number 4 here. And our purpose for providing steps number 2 and 3 is to give you the guidance, how to go from a free body diagram to writing the Newton's second law equation. And as you read through what Andrew Elby wrote in the portable TA, you can see how they do match up. So I feel like ours is a slightly polished up version of the strategy that he describes in the portable TA. So as you might have noticed when I drew free body diagram here, after you're done drawing free body diagram, if you're immediately trying to write down Newton's second law, especially in the component form, you're skipping a bit of a step here. What's your x direction? What's your y direction? And in his instructions too, Andrew, so I guess in this strategy, he's giving you something that's a bit of a one-dimensional thing, because he wants you to write Newton's second law along the direction of motion. So he's imagining defining one axis, x-axis, along the direction of motion of the mass. So we do that explicitly. We set up for that explicitly in step number 2 by identifying the direction of acceleration and using that to choose a coordinate system. And yeah, the coordinate system is chosen for each object separately, as you see him do here with these objects. So the mass on the ramp is accelerating this way, possibly. So that's the x-axis. The hanging mass is accelerating down, possibly. So that's chosen as the x-axis. And in order to write down this Newton's second law along those directions, you need to, so when forces are either along that direction or perpendicular to it, right? You have no additional work to do. But sometimes you will have some forces that are not in one or the other direction, but kind of diagonally. It's a combination of both the directions. That's where you do need to break it down into components so that you can see which direction of forces is perpendicular to the direction of motion and which direction is parallel to the direction of motion. So, so in step number 2, he says quite a bit here, and that's broken down explicitly in our steps number 2 and 3. And just one additional thing, he calls it a multi-block strategy. But if you have a single block, it's not multi-block, but you can use the exact same strategy. I guess the difference might be that a lot of you might feel like with many single object situations that you have enough intuition to get to the answer without going through this complicated strategy. And for many of you, that might be true. And if you are saying, all right, I just want to skip right to the answer, and there's nothing wrong with that. But what I want to caution you with is there are some questions where your intuition will fail you. You won't know quite what the next step to do is. And that's where this standard strategy really shines, because this is the detailed, systematic set of steps where you are able to follow from one step to next, and once again, each bite-sized chunk so that you can chew each piece without too much difficulty.